Alright, so looking at our do now, we see that there is a drawing below. We're given the equivalence, or the scale ratio is 4 centimeters to 3 meters. And we're given the length and width of the original scale drawing, which is 8 centimeters by 24 centimeters. So setting up our table here, our original input would be our scale drawing, and our output would be the real world. So throwing in the information that we know about this relationship, that this is 4 centimeters to 3 meters. So this y over x is 3/4. So we want to know what 8 and 24 would be in the real world, so we can find out what area is equal to what the length and width are in the real world. So our equation is y is equal to 3/4 x, and y is equal to 3/4 of 8, which is equal to 6. So in the real world, this one is 6 meters. And y equals 3/4 times x, which is y equals 3/4 times 24. And that's going to give us 18. So our length and width are 6 times 18. And that's going to be equal to 108 square meters. Alright, let's flip on over and look at our aim for today. Okay, today's aim, Kipsters will be able to identify and use the relationship between the areas of scaled figures. Kipsters will be able to find the relationship between the areas of scaled figures. Alright, identify and use the relationship. Forget the word use in there. Use the relationship between the area of scaled figures. Okay, so we're going to jump through a couple things here. We're going to look at this. We're going to start by looking at the scale ratio of 3 of these here. So when we're looking at our scale ratio, x to y, this is our input, this will be our output, is 3/4, so y over x is y over x is 3/6/3. So our scale ratio is 2. The actual area here is 12. Our scale drawing is 4 by 8. That's going to be 48. So the ratio of the areas, and so I'm looking for the ratio of the areas, is 48 over 12 is 4. And so what that tells me is that I can find, if I were to keep this same ratio from one figure to the next, the area of the second figure is 4 times the area of the original figure, or A0. Is the scale ratio the same as the area of the ratios? No, it is not. So that's something to keep in mind. We're going to see if this trend continues, but it looks like what we should be seeing here is that perhaps we can't exactly use the scale ratio to determine the area ratio. So looking at the second one, go ahead and do the same thing. See if you can't find the scale ratio, the actual ratio, the scale drawing area, the actual, and not the actual, sorry, this should be the ratio of areas. And tell me what the equation would be to find the area of a second figure based on the area of the original figure. Determine if they are the same. Go ahead and do that on your own. I'll give you a couple minutes. Alright, we should see our scale ratio. Again, just kind of thinking about this really quickly as a t-chart. 6 to 2, 6 to 2, that's going to be 2 over 6 is going to be equal to 1/3. Scale ratio should be 1/3. The area of the actual figure, that's this first one, 6 times 9 is 54. And the scale drawing here, the scale drawing area is 6 because it's 3 times 2. And so we're looking for the, again, this is going to be y because these are like our outputs, these are like our inputs, is going to be 6 over 54, which simplifies to 1 over 9. So the ratio of the areas is 1 over 9. Are the scale ratio and the ratio of the areas the same? No, once again, we see it as not. So what we should be seeing here is that we cannot use the scale ratio to find the areas. So I cannot take area 1 and multiply it by the scale ratio. I have to multiply it by the ratio of areas, which is different. So we should be able to make an assumption right now about this last one. Do you think the scale ratio is going to be the same as the ratio of areas? Hopefully you're thinking to yourself, no, this doesn't seem to be the pattern. So let's do one last to check it out. Our scale ratio, again, x to y. We're going from 6 to 8. So y over x is going to give me 8 over 6, which simplifies to 4/3. So when we look at the area here, remember this is a triangle, so it's base times height divided by 2, 9 times 6. We're going to see if that messes anything up with the triangles. 9 times 6 divided by 2 is going to be 54 divided by 2, which is going to be 27. The scale drawing area, that's going to be 12 times 8, which is 96 divided by 2, which would be 48. So our ratio of our areas, kind of again thinking about this is x and y, the inputs and the outputs, is going to be 48 over 27. Those are both divisible by 3. That's going to give me 16 over 9. The ratio of my areas is 16 over 9. So again, we go back and we look at that. No, absolutely not. 4 over 3 is not the same thing as 16 over 9. So no, they don't have the same ratio. The ratio I would have to use to find the area of a second figure given the area of the original would be 16 over 9. So is there anything that we notice about the ratio of the areas in examples 1 through 3? So I've given you a little table to kind of help you think this through. So let's go ahead and fill in the table pieces that we know. So we have the scale ratio for the first one was 2. The area ratio was 4. For this one, it was 1/3, and the area ratio was 1/9. And the last one, it was 4/3, and we got 16/3. In here I've given you kind of a place where I want you to figure out what we multiplied the scale ratio by to get the area ratio. Because I'm going to give you a hint. It's definitely a multiplicative relationship. So we have 2 times what is 4? Well, that's obviously 2. So you might be thinking to yourself, oh, well, maybe the point is that we're multiplying by 2. But multiplying by 2 would not get us where we needed to be here. We'd get 1/3 times 2 would be 2/3. So I'm thinking about this top times top. Well, to get the 1 on the top, I'd mean to multiply 1 by 1. To get the 9 on the bottom, I need 3 times 3. So it looks like what I'm starting to see here is maybe a pattern where the scale ratio, what you have to multiply the scale ratio by to get the area ratio, is the same. Sure enough, we can see here, if we multiply this one by 4/3, top times top, 4 times 4 gives me 16, and bottom times bottom, the 3 times 3 gives me the 9. So if the scale factor of the sides is k, so if we're calling this k, in order to get the area ratio, I need to multiply k times k, or if we think back to what we know about exponents, that's the same thing as k squared. So if we want to generalize how we find the area of a scale drawing, given the original area, we need to find that the area of the second figure is k squared. That's our constant of proportionality for the scale drawing times the area of the original. And we can use this equation in many different ways. We can use this equation if we're given the two areas. We can find the constant of proportionality, or the scale, if you will. Or we can use it the other way. If we're given the original area and we know the scale, we can find the area of the new one. Or we can find the area of the original figure if perhaps we're given the area of the new figure and the scale ratio between the two. So let's jump on over to our partner work time and see if we can't sort out some ideas of what this may look like. So before you get started, just want to explain really quickly that when we look at this, we are looking at a scaled figure from this figure to this figure. I'm asking you to answer through some of these questions. What is the scale ratio? So we should be able to figure that. There is enough information to figure out the scale ratio. It says what is the ratio of the areas? So we should be able to use that relationship that we just learned about, how we can find the area ratio based on the scale ratio. And if we're given the area, so we're going to have to use the equation for areas, kind of, once again, we just talked about. And then down there it's asking for the ratio, using the ratio of the sides to find a missing side. So go ahead and try this one out on your own. Go ahead and pause the video. Once you get it done, what you think, let's go ahead and walk back through what we see going on here. Great. Now that you've finished this, we're going to look at our scale ratio. So this is our original x and our y. So I'm going to think about this as a t-chart in between. I know that the original x is 1 and that 3/2. So this is going to be, the scale ratio is 3/2 over 1, which is just going to be 3/2. So what is the ratio of the areas? Well, we know that the ratio of the areas is the scale ratio times itself, or the scale ratio squared, which would be 3/2 times 3/2. And that's going to give me 9/4. So the equation for the area scale is that my area 1 is going to be equal to 9/4 times the area of my original. I'm told that the area of the original is 16, so I can find the area of the 9/4 times 16. Doing some cross canceling, that's going to give me that the area 1 is equal to 36 square units. Now coming down to this one, we're given a side, so this is not talking about areas. This is talking about sides. So we're going to use our original relationship. So we're thinking about y is equal to 3/2 times x. The missing side is 4, so I want to find its corresponding length. Y is equal to 3/2 times 4. Again, doing some cross canceling, we're going to get our answer here is 6 square units. Alright, so we've got a very similar problem coming down beneath. So try it out again on your own. If you need a quick start on this one, I think you might want to think about doing a drawing here really quickly. You have two shapes, one where it's 2 meters long and 1/2 inch as our starting points. So that can help you get started with your table if you prefer to use a table. This is 2 to 1/2. So y over x is going to be 1/2 divided by 2. Our scale ratio is 1/4, which means the ratio of the areas is 1/4 times 1/4. Which is 1/16. And so if we're dealing with the area of the first figure being 24 square units, then we know the area of the new figure is equal to 1/16 of the area of the original figure. So we're going to 1/16 times 24. It's going to give me 24 over 16, which is equal to 3/2, or 1.5 square units. For the sides, we're going to go back to just the scale ratio, where our y is equal to 1/4 times x. If the missing side is 4 units in the first figure, so my original figure, y equals 1/4 times 4, we get y is equal to 1, so it is 1 unit. Alright, come on over here. We're looking at this. We're going to, given the information for the suburban apartment, we're going to find the scale drawing area and the actual area of the apartment. So there's several different ways you can go about thinking about doing this, and actually you'll get to kind of choose on your own. Go ahead and work through this problem. Go ahead and pause this and then work through this problem, and we'll see what you come up with. Alright, so one way to go through this problem would be to set up an XY table. Go ahead and we can throw in that our relationship is 1 inch to 12 feet, X and Y. And we can see the length and width on our suburban apartment are 2 and 2.5. And so we could go through and we could do the work to figure out that what the x and y are. So we'd use y is equal to 12x. We'd figure out that y is equal to 12 times 2, should be 24. And this one would be y is equal to 12 times, that's going to be 5/4. which is going to be 3 and 15. And so then we could multiply 24 times 15. That's going to get kind of messy, but I think that's going to give us 360. And we'd have to find the original area. The area on the scale drawing would be 2 times 5 over 2, which would be equal to 5. So 5 and 360. So, but there's an alternative way that we could do this. Is we see that the ratio here, the scale is this. So we can use what we know. 12 times 12 is 144. So we could write the area formula is A1 is equal to 144 times the area of the original. And since I had to find the area of the original was 5, I could multiply 144 times 5, and I'm going to get the same result. It's 360. So we can see that there's really two ways to go about doing this. It's really just a matter of what you think is faster or what you think is easier. The reality, though, is that you do need to know how to use this equation or find that relationship between the areas given the scale and the lengths of the sides. All right, please go ahead and move on to your silent and independent work.